We are continuing our discussion of properties of determinants. We're on page 3 of the handout, right, for 3.2. And theorem 4 is of enormous significance. A square matrix A is invertible if and only if the determinant of A is non-zero. So certainly invertible matrices are important, or being able to tell if a matrix is invertible or not has some significance. And so here's one way to attach some meaning to this determinant calculation. Like, what is this determinant thing? Well, if the determinant comes out to be non-zero, we know the matrix is invertible. If the determinant is equal to 0, then the matrix is not invertible. So this result we can actually add to the list in Theorem 8. Remember that Theorem 8 with the A, B, C, D, E, F, G, H, I. It's like this is a J, or in the book probably gives it some letter along the way. It can be added to that list of equivalences, determinant of A non-zero. And this is important enough that we're going to talk about the proof a little bit, about how this theorem would be proved. So suppose A is a square matrix. We can convert A to echelon form. Let's not worry about reduced echelon form. So the pivots might not be 1 by using 2 of the row operations. So if we don't worry about getting 1s, we can get to an echelon form by just adding multiples of one row to another and interchanging 2 rows. So we're not going to multiply or divide a row by a constant. That's what we would have to do to get the 1s in position. So if we let U denote the echelon form of A, then the determinant of A is going to be plus or minus 1 times the determinant of U. And the plus or minus 1 depends on how many times we multiply by -1. That's by how many times we've interchanged rows. And we're not worried about how many times. So the only way the determinant value changes is by that row interchange, because when you add a multiple of one row to another, that does not change the value of the determinant. So again, we're not allowing the row operation where you multiply or divide by a constant here. So if A is not invertible, then U will have a row of zeros. So that echelon form will have to have a row of zeros. So the determinant of U is 0. And so the determinant of A would be, plus or minus 1 times 0, which would also be 0. And therefore, if the determinant of A is not 0, A must be invertible. Because if A is not invertible, the determinant of A will be 0. Now, conversely, what if we know A is an invertible matrix? Then we know that the echelon form of A will have this kind of a form, which is upper triangular. The pivots are all non-zero. We're not worried about 1s here again. Pivots are all non-zero on the diagonal, of course. It's not necessarily 4 by 4. This is just meant to represent the general situation, but the size could be any size n by n. But by theorem 2, the determinant of U is going to be from this chapter, theorem 2, the determinant of U is the product of the pivot entries, which are all non-zero. So the determinant of U must be non-zero. The determinant of A is going to be plus or minus the determinant of U must also be non-zero. So it's really this row operation connection that helps us understand why the determinant of any invertible matrix is not 0. Okay, next page, theorem 5. Important, not quite as important, but worth mentioning. If A is a square matrix, then the determinant of the transpose of A equals the determinant of A. That should seem, we've kind of hinted at that because we said you could expand along a row or along a column, so that the determinant of a transpose always comes out the same as the determinant of the original matrix. What this means is that we actually could allow column operations. This is something we have not used at all in this course yet, row and column operations, to simplify a matrix before calculating a determinant. So we can use what are called elementary column operations to evaluate determinants. Now, I'm not going to use that in the rest of the course. You may, but I'm not going to, because I think students sometimes find that confusing. There are lots of situations where we can only use row operations. Like when we're solving a system of equations, we can only use row operations. Elementary column operations are only allowed for determinant calculation. So I'm just going to never use column operations, basically. But I just want to mention the fact that that's a possibility. The proof of Theorem 5 I'm not going to talk about with you. It's written out here. It involves something called mathematical induction. And so it's a little bit tedious, but you can read it. You're not responsible for it. In fact, it continues on to the next page. And again, I tried to write it out on the handout in a way that would be readable and understandable, but it is a little bit dense, so it's okay if you don't follow it. Theorem 6 is the second super important. So Theorem 4 and 6 are so very important in this chapter. Theorem 6, if A and B are both n by n matrices, then the determinant of A times B is the determinant of A times the determinant of B. To me, that's kind of an amazing observation. Determinant is this complicated calculation that gives us a number associated with the matrix. When we multiply two matrices, they get sort of like intermingled, tied together in a crazy way. And yet the determinant of that product of those two square matrices will always be equal to the product of the two separate determinants. It's just amazing to think about that. So the determinant of the product is the product of the determinants. There's no similar theorem for matrix addition. In general, the determinant of A plus B is not equal to the determinant of A plus the determinant of B. Now, I say here we'll not prove theorems 3 and 6, but I have posted my version of the proofs of theorem 3 and 6 because theorem 6 is so deep somehow. I thought it would be worthwhile to write out the proof. But my version of the proof is like 10 pages long or something. And so it's posted. You can, just for the people who find that kind of thing interesting, you can take a look. But don't worry if you don't. It's not required. And finally, one more theorem here. If A is an invertible matrix, the determinant of the inverse matrix is 1 over the determinant of the original matrix. And I'm not going to prove that here because that's a homework exercise, I think. And so you guys will have to figure that out or ask me for help if you're stuck on it. So we have some more exercises to do, and I think this will get us to the end of this section. I'm going to leave these exercises for the next part of the video. I'm going to cut it off here with this part.